This is how this would be implemented. I won't go into too much details. But again, we can start off the batching, the types and sizes of batches. You can pre-compute all of this beforehand statically. This needs to be done dynamically. So again, it's going to be packed here, and you can simply iterate through the size of the batch and then do the setup. And so the key thing here is so the less batches and everything pre-sorted, as I said. But the key point here is this loop inside. This is the dispatch. So this is completely parallel at this point because what you're doing is executing over a batch. And so on the next slide, we can see that we can do some setups for the solver kernel here. It's using the C++ API, and because now you can get it all on the same one slide rather than 10 slides. But and then at the bottom, which is the most important bit here, you can see that just because we want to have the work group size in OpenCL needs to be a multiple of the global size. The global size, sorry, needs to be a multiple of the work group size. So we just do some rounding up just to take account of that. Otherwise, you might get an error with this batch. And then you can see that we simply replace that for loop and now become the grid that we're going to launch around over to do the parallel execution of that. And so for every batch, we do this iteration here. So we replace that. The kernel itself is very straightforward. You can see that it takes all the things you'd expect. It takes a start link, a number of links, and then it takes some constants, and then it takes all the buffers that we're going to be updating during the solver and so forth. I mean, there's no real rocket science. Here, there is a important point at the top here. Because we round it up, we can't, actually, we don't want to overdo the amount of work. And so if our global ID, so the loop bounce that we're doing, is actually greater than the amount of work, number of links that we've actually got, we don't want to do anything. It is possible, and we were talking about this just before, Lee and I, that you could think about actually padding the links, and then you wouldn't need to do this testing. So you do some redundant work, but the assemblies are doing some redundant work anyway. That might be more effective because then you aren't doing any masking or anything like that with your assembly machines. But that's still something for us to explore. And that's what it means by that. And again, this is pretty much, if you went back and looked at the CPU code, you can pretty much see that this is one-to-one mapping. And so often, once you've worked out, and this is really what I want to stress, once you've worked out to break down your program to give you the parallelism that you need, and you do need to do that if you're going to use, whether it's a many-core CPU, but particularly with GPUs where you have got a huge amount of parallelism, but to get them to run efficiently and not sequentially, you do want to break that apart. So then you're pretty much picking up the core of your algorithm and sticking it across. I'm not saying that's always the case, but it's often the case. Okay. So I've shown you a bit of the CPU code, and that was our kind of second attempt, second implementation, and it has many benefits about it. But the one thing it has is that we talked about 10 batches that appeared from this one here. This is only a few things, and every batch is an incube. It's a dispatch, and it's not cheap. You've got all the PCIe, startup time, all of those sorts of things. Sure, the runtime will probably batch some of those things together, and Yaki can show that on one of these things. You can actually see that happening on our runtime, and we'll batch things together, so you won't always pay that cost. It's still not going to be free though. You're still having a global synchronization point. So maybe we want to reduce that. So let's get a single work item doing more work. That would be the first thing we do. So here we're going to say that. So here we're going to create larger groups of the batches. So basically we're going to start making the batches bigger. And each of these colours here, the links here, will be done by a single work item doing that. So we can do fewer dispatches. So here we've gone to 9. And we can go down to 4. We can go down, we can reduce that. And I think, so I haven't got it. Sometimes we go down to 1 batch, but I'm sure that would be a mistake or not. But basically, now we've really improved the efficiency within a single work item. And there will be some problems with that. The problem being, of course, is that we've now reduced the amount of overall parallelism that's going to be happening in the SIMD node. So if we were using 10 SIMD cores, we'd never reduce it to create any full batches. Maybe we're only using 2 SIMD cores now. So that, that's 80% of the GPU not being used. And so again, you've got this problem. The obvious solution to that is to solve multiple clocks together. Often you're going to want to have, we had a really nice demo at GDC where we had this samurai kind of stadium, and there was all these flags and cloths, and then there's the cloth on the samurai guide together. They're all being solved together, and you can put them in and batch them up together to create a Lugo cloth. There's a common technique happening there. And so and then of course you get this work distributed. So it's just a way of kind of batching up work and then distributing it inherently by the algorithm itself. Cool. Okay, so I've got enough time. Okay, so that's kind of where we were for a long time, and Lee and others and myself and others, we discussed this quite a bit, and we kind of think this is a reasonably effective implementation. You know, and you can get a lot of, even with this, I think, you know, we can have, you know, we can run, you know, hundreds of pieces of BOF on a GPU. But is it really using the most efficient way? You know, what happens if we wanted to do something else on the GPU at the same time? You know, so maybe we wanted the BOF to be even more efficient, so that we only have 10 pieces of BOF, but then we can be doing a fluid or some rendering. So, you know, so this is where we got to, and so here I put a SIMD. We've got SIMD at the top of the thing. So now we're going to start talking about, in our programs, in the code that we write, the width of the SIMD. So you know that the SIMD is different on the two different architectures, you know, two different vendors. So this code will not port between those different codes. Now we're not talking about portability, we're talking really about optimizing for the SIMD width of the machine. But it can resolve this issue. You know, we can walk away and we can say that you don't need to solve serially for each link. You know, one of the problems is that you know, you have each group doing these things, but you can only do so much of the batching because you're batching across the whole of the dispatch. What happens if we just batched at the SIMD level? So what would this mean? So taking one of the groups from our previous thing, let's say we just batch this. And the key thing about this is that each of each of these nodes here in that batch is being mapped to a SIMD core. And you're guaranteed that that's always going to be done as one operation, because it's a SIMD machine, and so that's going to be done. So each of this can be solved. It has no dependencies. If there's another one coming in behind it, there's nothing stopping that from being thrown out and that one being executed, so you can hide memory latency, all of those things. You know. And here you can see that, of course, we still need to batch, but now we're batching within the SIMD only, and these batches can be processed by a single kernel. It doesn't matter, they can be run on any core independently. You know, you just group them up. And the really great thing about this is that, you know, each work item is basically running around this little loop, working against a set of nodes, but because it's completely independent, we can just unroll the loop and just have a straight, direct piece of code. We haven't got any masking or anything like that. And so I think it's without a doubt we've sacrificed something by losing the portability between two options. Obviously, it's not that difficult to put some counterparts and put those things in, but we're not doing that. We're not that difficult. It's just a bit tricky. But there is a huge benefit, and I can't remember the exact performance numbers, and we're still going through the final implementation. But we are talking, you know, factors, you know, of like 5, maybe even 10 performance benefits over the other ones. You know, so there is a considerable thing to be considered here. And so, I don't want to be too negative about what you can do already, but I'm just trying to give you, you know, if there is this opportunity, if you think about how your algorithm is broken down, it's really constructive. But now I'm going to pass it over to Yaki, who's going to show you a demonstration of that flag demo and everything, and show you a little bit about how you might debug it and then use their excellent tool.
Hi everybody, I'm Yaki from Graphic Remedy. Show the demonstration of close animation. We see 3 eras of computing. First, there was the single core era, in which you wrote your program. If the CPU advanced, then you get the benefit for free. Can you hear me? Then there was the multi-core era, when you need to write multi-threaded applications to gain the performance value. And now we have heterogeneous systems which has CPUs, GPUs, DSPs, and all kinds of horsepower under them, and you need to adjust to new APIs like OpenCL to take advantage of that. So this is quite fun. It's a new way of programming. You have lots of horsepowers, but it has also a very big drawback, which it's very hard to do debugging and profiling on those heterogeneous platforms. And we see that companies find it really hard to deliver applications on time. And it's really, really, really hard to optimize the application to take the full advantage of the horsepowers that you have. So we offer a tool called the GDebugger. It's a debugger and profiler and memory analyzer for OpenGL, OpenGLF, and OpenCL. and it basically provides information a developer needs to find bugs and optimize performance. So I think I'll dive into a demo.
Okay, so let's just... That's me when I was young. There you go. It's just a...
What you see there is the kernels are compiled. So it's loading and unloading the compiler. And it runs through. This is the both demo, the flags demo that Ben talked about. You can see the both flags. They are simulated and rendered in OpenCL. So this is kind of handy and nice, and has very nice performance. Switch over to GDebugging. When you break the application run, I'll first talk about a few debugging features and then about profiling features. So you can see the call flow. These are the calls that made into the OpenCL API. You can see each call and its arguments. If you're having textures or buffers, this opens on the other screen, I guess. Break the right screen. So if you're using textures or images, these are the OpenCL images. So if you select one, and you can see this is the image, you can see its properties, you can see its data, it's raw data. So if it's the buffer, that's interesting. And you can see that this image, this OpenCL image is associated with texture 1 from OpenGL context 1. So if I switch to the OpenGL context, then you can see the exact same objects which are actually OpenGL objects now. So we display very nicely the OpenGL and CL interoperability. Let's switch back to the CL. If you are using buffers, like this one uses quite a lot of buffers, then you can see the buffers data. And we also have an extension that allows you to name them. So if you have, like here, quite a lot of buffer, you know each buffer what it represents. So you can see the raw data of the buffer as it is online as you whenever you suspended the application. This one. Here we display all the programs and the kernels that are loaded. And for each program you can see its source code, and you can see the kernels that are inside, and you can see the properties. And you can do something nice like that. So you can edit it, and then you can build it on the fly. Okay. And then you can render, and you can see that there is a nice effect on the cloth.